In this lesson, we're going to explore how we can calculate the change in entropy for a system undergoing a phase change. So for example, the change in entropy of ice as it melts into water. And we're going to use this equation to measure this entropy change, where delta S is the change in entropy of a system, for example, a melting ice cube. T sub m is the absolute temperature in Kelvin at which the heat transfer occurs. Delta Q sub R is the infinitesimal amount of heat added or removed from a system in a reversible process. And we integrate this to get the total change in entropy. So with this equation, if you were to make an educated guess before plugging in some numbers here, what would you expect to happen to the entropy of the ice water as it melts? Would the change in entropy be positive, negative, or would the entropy remain constant during this process? Well, ice has a lower entropy state than the equivalent mass of liquid water because molecules of liquid have many more ways to arrange themselves than the same molecules when they're locked up in a lattice structure. So with this in mind, we'd expect the entropy change to be positive. So first, we're going to assume that the ice cube melts so slowly that it can be considered a reversible process. For a process to be reversible in thermodynamics, it needs to happen in such a way that each step of this process or in the process is nearly in equilibrium with its surroundings, allowing it to be theoretically reversed. We also know during a phase change, the temperature remains constant, so we can remove the temperature outside of the integral sign. Now, because we're approximating this as a reversible process, we can use the equation for the latent heat of fusion to work out the total amount of heat transfer required to fully melt a mass of ice. And this value would be positive when we're transferring heat into the ice. If we were cooling the ice, heat would be flowing out into the surroundings, and this would result in a negative change in entropy for our ice cube. So let's say our ice cube has a mass of 50 grams or 0.05 kilograms. And we can also look up the latent heat of fusion for water, which is around 300,000 joules per kilogram. We can then divide this by the temperature of ice as it's melting, which is 273 Kelvin to 3 significant figures. So after we plug this into our formula, we get an increase in entropy of a positive 61.0 joules per Kelvin to 3 significant figures. Now, when we're doing calculations like these, we must remember that systems can have positive or negative entropy changes depending on whether heat is transferring into or out of the system. But the change in entropy for the system and the environment combined will always be positive for real, irreversible processes. And we'll cover this in the next lesson.